So we're continuing with exercise 1714 here in trying to predict the products of a couple Diels-Alder reactions. So in this one, let's line up those molecules so we can sort of see them like we were seeing them before. We have our diene on the left, which is S-cis, right? Remember that you've got your 4 parallel p orbitals here, and because of that, the electrons aren't just located right there, they fly over the whole thing, all 4 of those p orbitals, and so this bond right here, in between the what look like the 2 double bonds, this bond right here isn't just a single bond, it has some double bond character. And so it's hard to get that to rotate because the 2 p orbitals that are here the electrons can only fly through those if they're parallel. And so if that bond there tries to rotate, they're not parallel anymore, and you would break the conjugation. So even though it's a single bond, it doesn't rotate very well. You'd have to heat it up a lot in order for it to rotate. And so it looks like a single bond, so it's called S, but if you draw the dotted line around it, you have 2 things going on the same side of that double bond, so it's called S-cis. And if they were going on opposite sides, it'd be called S-trans. In order to do the Diels-Alder reaction, the diene has to be S-cis. Otherwise, the orbitals, the LUMO, the lowest unoccupied molecular orbital on the dienophile, wouldn't be able to reach the 2 ends of the conjugated pi bond system of the diene. So we'll draw that diene S-cis, and then we'll draw our dienophile, but with the double bond very clearly aligned to where we need it to be. So 5-membered ring, and then right next to this we've got our ketone. Okay, so first step, draw in those circles at the end of the conjugated pi system of the diene, and also just dots at the end of the double bond between carbons on the dienophile, and connect those with dotted lines. Now if it helps, you could number these. So number the carbons in the diene, number the carbons in the dienophile. And I'm going to color the pi bonds. It's the pi bonds that are going to be moving around. I'm going to color the electrons in those pi bonds so we can sort of trace them as they move a little bit better. So here I'll have purple on top and then this dark blue one at the bottom. All right, so you can take once you've sort of got this format written out, drawn out, you can take those pi electrons and you're going to move them all in a circle in the same direction. So here I'm going to move them all clockwise. So I'll move that one clockwise, the next one clockwise. Let me make that a little clearer. And then this one clockwise. And you're moving them all 1 bond over in that clockwise direction. So if you take those same pieces, let's just take the carbons that are going to involved in this cycloaddition, and then we'll worry about all of the other stuff in a second. So looking at that, if you take that purple bond, that's going to go from being between carbons 1 and 2 to being between carbons 1 and 6, so that forms that sigma bond there. If you look at the green electrons, that's going to go from being between, those are going to go from being between carbons 5 and 6 to being between carbons 4 and 5, so that goes to form this other sigma bond. The dark blue pi electrons, that goes from being between carbons 3 and 4 to being between carbons 2 and 3. So you form that new pi bond. And there's your ring. So that's the cycloaddition. Now we just need to think about the electron withdrawing group and the rest of the molecule that's coming off of the dienophile here. So that is the dienophile has a double bond. If you draw a dotted line going down the long end of it, you will see that on the top you have a branch going to the right, and on the bottom carbon you have another branch going to the right. So both of these branches are on the same side of this dotted line, and so this is going to be cis. So however we draw those branches coming off, they need to be going on the same side. So for example, you could have them both going away, or you could have them both coming out at you. Here I'm going to put them going away with those dashes. So then we'll just add that extra carbon in, and here we'd have our ketone. And so that would be your product for this Diels-Alder reaction. All right, next one, H. So let's redraw these molecules so that they're lined up in a way that makes it easier and more intuitive for us. So we'll have that triple bond right next to that diene there, so we can almost see the ring. And then we'll add in that carboxylic acid, which is the electron withdrawing group. So once you've got them drawn up in this aligned sort of way, draw dots at the end of the diene and at the end of the carbon-to-carbon pi bonds in the dienophile. And you could number these if it helps you to keep track of them. We'll number the carbons in the diene and the carbons in the dienophile. And I'm going to draw the pi electrons here. They're going to move in different colors so that we can sort of track them. And notice that in the dienophile here, in the dienophile, it's only one of the pi bonds that are going to be moving. The other pi bond is going to stay right where it is. So now we can draw those dotted lines between the ends of our molecules, and we just want to take those pi electrons and move them all clockwise. So here I'm going to move all of those one bond over clockwise. So now I can draw those pieces one more time. And let me just number those so it's easier for me to keep track of what's going on. And the purple pi electrons here are going to go from being between carbon number 1 and 2 to being between carbon number 1 and 6, so they're going to move up here. The green electrons are going to go from being between carbon 5 and 6 to being between carbon 4 and 5, so they form that sigma bond there. And then the dark blue electrons are going to go from being between carbon 3 and 4 to being between carbon 2 and 3, so they'll form that new pi bond there. Notice that we have another pi bond between carbon 5 and 6. That stays. And because there's a double bond here, both of the carbons, both carbon 5 and carbon 6, are sp2 hybridized, which means that they're trigonal planar. And so the branch here isn't going to be coming out at us, it's not going to be going away from us, it's going to be in the plane, planar. So we'll just draw it as a regular line. So this bond here is just a regular line because the atom it's bonded to in the ring has a double bond, which means it's sp2 hybridized and trigonal planar. So that there is the beautiful product you'd get if you did this Diels-Alder reaction. Last but not least, for 1714, we'll take our two pieces, and they were nicely lined up here, so we can just draw the dots at the end of the conjugated diene, and the dots at the end of the carbon-to-carbon pi bond in the dienophile, and we'll draw dotted lines in between those. Just so we can keep track of them, I'm going to color the pi bonds here, so we can watch them as they move around to form this ring. And once you've got all of that, and why not, let's just number these so it's easy for us to keep track of everything. So once you've got this, I'm just going to move all of these pi bonds, the electrons in those pi bonds, I'm going to move them all clockwise, one bond over. So now we will draw our carbon skeleton for the diene, the carbon skeleton for the dienophile, number them so we can sort of think about it more clearly. And here, the purple pi electrons are going to go from being between carbon number 1 and 2 to being between carbon number 1 and 6, so they form that sigma bond there. The green pi electrons are going to go from being between carbon number 5 and 6 to being between carbon number 4 and 5, so they form that sigma bond there. And then the blue pi electrons are going to go from being between carbon 3 and 4 to being between carbons 2 and 3, so they'll form that new pi bond there. Now we just have to worry about the electron withdrawing group and what direction that's going in. So here, it could either be coming out or going away. There's no real preference for how that would happen. So we would either get a molecule where, in here, let me actually take this. We have two possibilities here, so I'm going to do that. Either this group will be coming out so you'd get that, or you'll also get that going away. Because this is a chiral center. This atom here is a chiral center. So it could either be R or S. It could either be the right-handed version or the left-handed version of itself. And so you get both of those versions. And you get that by having the opposite orientations there. And so those would be the solutions for that really cool, fun, awesome, amazing Diels-Alder reaction.